So here's all the points that I have highlighted for this question. So let us start with 2A first. So for 2A, the question gives to us B, magnitude of magnetic field is 0.2 Tesla. And it said that magnetic field is parallel to the plane of the circular loop with radius 0.2 meter. So radius given is 0.2 meter. So the question asks us to determine the magnetic flux through the loop. I tried to sketch the figure, a diagram to represent how the circular loops is parallel to the magnetic field. So let's say this is the plane of the circular loop that I try to sketch here. So our B now is parallel to the magnetic field plane, and we know that this is, let's say, the B, and we know that the plane, the vector A, is always perpendicular to the surface of the circular loop. So from here you can see that theta between vector A and vector B is 90 degree. So when we calculate the magnetic flux, we using the formula magnetic flux equal to BA cos theta. So we have the B given is 0.2. The area, since circular loop is circle shape, so we use a formula area pi r squared cos 90 degree. Therefore, the magnetic flux is actually 0. Because what? Because B is parallel to the plane. The cos theta is 90 degree. Let us proceed our discussion with question 2B1. When we read this question, the question is regarding a coil. We are given the numbers of turns. We are given the area of the coil. It mentioned here the coil experience changing in magnetic field. We are given the rate change of magnetic field. Due to these changings of magnetic field, induced EMF is produced in the coil. Therefore, the questions ask us to calculate the induced EMF in the coil. So that's roughly the idea what the question is all about. So when I read the questions, I have highlighted the information. Now I have also listed down all the informations given. We have coil case now, and then the numbers of turns given is 100 turns here. The area given is 0.5 cm square, but we need to change it into meter square, so make sure you times with 10 to power of -4. And it mentioned here the rate of change here. The rate of change magnetic field is 1.08 Tesla per second. So to write mathematical, to express the rate of change magnetic field is we need to write as dB over dt. The questions ask us to determine the induced EMF. So before we proceed this calculation, let us recap together the concept that we need to know if we have a coil case. We need to think first, what is the equation that we need to use? What is the equation that we need to choose in the list of formula? So the coil case here, actually we need to know the coil will experience induced EMF, or I just write as EMF, due to the two changes. The first one, induced EMF can be produced if the coil experience change in magnetic field. Number 2, the induced EMF also can be produced if the coil experience the change in area. So you have to choose which one the changes in the questions, right? So for this question, actually is due to the changes in magnetic field. So the formula that we need to use is EMF equal to negative N A dB over dt for this question. And if the other question mentioned that it experienced the change in area, so the formula that you need to choose in your list of formula is EMF equal to negative N B dA over dt. So for this question, we need to choose this formula. Okay, let us write again the formula. EMF equal to negative N A dB over dt. We substitute the value 100 turns. The area is 0.5 times 10 to the power of negative 4. dB over dt given 1.08. So press your calculator, the answer should be 5.4 times 10 to the power of negative 3 volt. Let us continue our discussion with 2B2. When I read this question is still about a coil, but the difference from previous question is the coil now is rotating with frequency 90 Hz given in the questions. We don't have numbers of turns. We are given the area. We are given the uniform magnetic field and the magnitudes of maximum induced EMF. The questions ask us to calculate the numbers of turns. So here's I have listed all the informations that we have. We have the area, frequency, magnetic field, induced EMF. Okay. Now, the concept that we need to know is this induced EMF maximum produced if the theta is equal to 90 degree. The theta here is angle between vector B and vector A. So the question asks us to determine the numbers of turns. The numbers of turns. So the suitable formula that we need to use, induced EMF is equal to NBA omega sine omega t. We need to know that this omega is equal to 2 pi f, and this omega t can be replaced by angular displacement, which is theta here. So I want to substitute all the informations that we have in the list of informations that we have listed down. I have n turns, B is 0.28, the area given is 6.8 times 10 to the power of negative 2, the omega is 2 pi times with the frequency is 90. So the sine theta here I can replace with 90 degree. So we press our calculator, the numbers of turns, make it n as your subject. You got 11.93, so it's approximately to 12 turns. Alright, I hope all of you still with me. I'm going to discuss the next questions, 2C. 2C1 and 2C2. So we read the questions first. This question is about a solenoid. Given the radius, the numbers of turns, the length. The questions ask us to determine the inductance and also the rate at which currents must change in order to produce induced EMF equal to 50 millivolt. So I focus on the first informations given. The radius given is 5 times 10 to the power of negative 2 meter, change to meter. Numbers of turns is 200 turns. Okay, don't forget the case is solenoid here. Okay, given the length is 15 times 10 to the power of negative 2 meter. We need to calculate the inductance. So this is 1 for 2B. Right? So to calculate L solenoid, we need to use a formula L solenoid equal to mu naught n squared E divided by L. So mu naught, as usual, we can get from the list of constant. The numbers of turns given is 200 turns, so square. The area, what is the area? Since it's a circle, okay, the area for circle should be pi r squared. So it's pi times with 5 times 10 to the power of negative 2 square. And we need to divide it by the length here. The length is 15 times 10 to the power of negative 2. So when we press our calculator, we got 2.63 millihenry. Next question, 2C2. When we read this question, we know that the question is regarding to self-induction, self-inductance, because it mentioned here the induced EMF is produced. We need to calculate the rate at which currents must change. So I have here EMF equal to 50 times 10 to the power of negative 3 volt, and this EMF produced due to the changes of current in the same solenoid. So it's referring to the self-induction process. Okay, referring to self-induction process. And due to this process, we will have self-inductance, and the related formula that we need to use to answer this equation is EMF equal to negative L di over dt. Means that the current change in the same solenoid, and when it's changed the current, the solenoid will experience the change in magnetic field, so induced EMF will produce. I have the EMF given in these questions, and also we have calculated the inductance. So 50 times 10 to the power of negative 3, we are referring to the magnitude, therefore the sign here will be make it as positive. So the inductance from previous question is 2.63 times 10 to the power of negative 3, and we have di over dt. So you make it di over dt as your subject. You press your calculator, you should got 19.01 ampere per second. Let us discuss our last question 2D. So we need to read first and highlight the information as usual. So I list down all the informations given. Actually, we have given the numbers of turns, right? So N1 is 350 turns. N2, secondary coil, 200 turns. And it mentions that current in the primary coil, so I1 equal to 6.5 ampere. The average magnetic flux through each turn of the secondary coil is 0.018. So that will be magnetic flux in secondary coil equal to 0.0818 Weber. We need to calculate the mutual inductance. To calculate this mutual inductance, firstly, we have to know about this concept. M12 equal to N2 times magnetic flux 2 over I1. M21 is equal to N1 times with magnetic flux 1 divided by I2. And mutual inductance in M12 equal to M21 actually. So I can just represent it with capital M. So the concept here is changes of current in the first coil will lead to produce changes of magnetic flux, and these changes of magnetic flux will be experienced by the second coil. That's the process of mutual induction. Alright, so based on this information that we have listed down here, so the most suitable formula that I can use is this one, because we are given the I1. So that M12 I just replace with M, N2 times with magnetic flux 2 divided by I2. I just substitute the information. N2 is 200 turns, magnetic flux 2 is 0.018 divided by I1 6.5 ampere, and our mutual inductance is 0.55 Henry. Alright, we go for the last questions 2D2. In these questions, we need to calculate the average flux through each turns of the primary coil. So I need to have magnetic flux in the primary coil. So 1, I make it as subject that we need to calculate. When the current in the secondary coil is I2 is 1.5 ampere. Then back to this equation, which equation suit with the informations given here. So we need to use the equations of I2. So mutual inductance equal to N1, magnetic flux 1 divided by I2. We need to determine actually magnetic flux 1. Okay, so magnetic flux 1, if we rearrange the equation, so M times with I2 divided by N1. So mutual is what we have calculated in the first part, which is mutual induction should be same here. So M just now we got 0.55 Henry. Current I2 is 1.5. The numbers of turns is 350. So the magnetic flux in the first coil is 2.36 times 10 to the power of -3 Weber. That's all from us. All the best for your final PSPM.